Hello, thanks for the joining this eSeminar. Today, I would like to talk about one of the important industry process, chassis and suspension strength and durability. My name is Youngwon Han. I am SIMULIA Senior Industry Solution Manager. I will talk the first half part of this presentation, and Jaewon Choi, who is a SIMULIA expert solution consultant, will talk about the rest of the presentation. When you consider the current industry trend, you can easily find the following four business drivers: electric, connected, and autonomous vehicles, new customer experience, quality, cost, and regulations, and mass production to mass customization. All of these business drivers are related with chassis and suspension. The new electric vehicle requires the new process of the vehicle design. Due to the simple configuration of powertrain, the development time of the vehicle is shorter, and one platform for variation of vehicles are demanded more and more. Rule of handling, right-hand handling of the customer experience cannot be satisfied at the same time. Trade-off is necessary, and the high expectations in the new electric vehicle is also challenging. Like other vehicle systems, chassis and suspension contributions to the ever-growing challenging to meet the quality and regulatory requirements while reducing cost. It is also tough to validate the chassis and suspension system for all vehicle variants. In order to meet the new specification and demand to managing all vehicle variants, one platform concept is very attractive, but the development of the platform is challenging due to the developing cost and time. And considering the weight of the battery in the electric vehicle, for example, the reduction of the unsprung mass is more demanding. Also, the ride quality is better by reducing the unsprung mass. The most challenging topic is to control the quality while satisfying all demands, such as the lightweight, efficiency, vehicle safety, and etc. In order to meet all the structural requirements which are related with the above challenging that I mentioned before, DS provides the chassis and suspension strength and durability industry process. Here's the expected outcome and benefit to use chassis and suspension strength and durability industry process. First, let me summarize the engineering target we mentioned so far. Managing multiple variants, increase engineering process efficiency, reduce the vehicle weight through component lightweighting, reduce unsprung mass through lightweighting, ensure vehicle safe operations during abuse events, validate structural integrity of suspension system and components, correlate simulation and test results. Once these targets are met, the following outcome and benefits can be achieved. First, faster time to market. Second, reduce components and vehicle weight, and finally, limit failures, recalls, and warranty cost. For faster time to market, the 3D Experience platform enables increased collaboration efficiency through the development process. As you can see, it provides the seamless interaction between CAD and CA data. And this can provide the saving times for exchanging the data, for example, 2-3 days to 1 day. And also, it provides great functionality to select the various results of the various the parameter of the design and choose the optimal design. And also the another great functionality in 3D Experience is it enables to deliver the digital continuity by carrying the information in each step of the development process from concept design to the final validation. The SIMULIA also provides the advanced tool to help engineers deliver optimum design fast while retaining confidence in their performance. By topology or parametric optimization, the engineer can easily decide which topology or parameters are the best for the components in the system. SIMULIA can also provide the technologies that predictably access component and system performance without the need to build a physical prototype. The best-in-the-class structure solver with advanced functionality can cover various KPIs such as stiffness, strength, stress, and strength and stress. Considering the large articulation and deformation too. The fatigue life tool can predict the spot and seam word, and it is validated with more than 3,500 physical fatigue test results. The best-in-class structure solver with advanced functionalities can also simulate both components and the full system of the suspension accurately to predict the real load cases. This enables cost saving for the physical test. In this industry process, the user can achieve various KPIs. The 3 business KPIs that you can see on the right top detect issues in early stage, reduce cost, reduce warranty costs, can be easily achieved by acquiring the several performance KPIs that you can see on the left. The improved ride and handling by engineering the suspension components with the desired stiffness and strength. Design the subsystem to satisfy the required stiffness, strength, and fatigue life. The permanent deformation after abuse load cases and decrease the weight through multi-objective optimization and more alternative evaluated through the design-driven automated simulation model. The performance KPIs that I mentioned will make it happen when individual technical KPIs and that you can see on the right bottom are met, which is efficiently predict the large articulation deformation and accurate model the full suspensions for predicting the durabilities, reliable prediction of the failure of abuse case, and evaluate the trade-off between performance and weight. And this slide shows the various references which which are evidence of the DS solution are really working in the vehicle development project in various automotive OEMs. Now I will pass the board to the Jae-Won Choi, who will explain the detail of the workflows in this industry process. Jae-Won.
Hi, thanks Young-Won for the very nice introduction of this eSeminar presentation. Hi, my name is Jae-Won Choi, and I will take over from now on. And I am sitting in the Dearborn, Michigan office, and I am working as the Senior Expert Solution Consultant. And my major part is actually material modeling and the method development especially around the plastics and the rubber materials. So as Young-Won explained so far, in order to meet the customer's needs on chassis and suspension strength and durability for the transportation and mobility, SIMULIA developed 6 main workflows around chassis and suspension of a vehicle, as shown in this slide. So SIMULIA also developed or is developing other workflows such as the tire engineering, brake system engineering, body NVH, exhaust system engineering, and vehicle dynamic performance. And I will not touch in detail for that related industry processes, but I will focus on the 6 workflows developed for the chassis and suspension strength and durability for transportation and mobility. Next slide, please. So to recap what Young-Won explained so far, I want to talk about the overview of chassis and suspension strength and durability workflows with respect to the design stages and their interactions with our other workflows we developed or are developing. During the concept selection and the preliminary design stages, customer can adopt material calibration workflow to build material database. It can be applied to a new material and also to improve the calibration accuracy of old materials. And results of material calibrations can be used by component optimization and component large deformation workflows, and also can be used in joint analysis workflow during preliminary and detailed design stages. Then all of the results of component optimization, component large deformation, and joint analysis workflows can be transferred to subsystem durability workflow to assess subsystem durability and optimize it. All of component optimization, component large deformation, joint analysis, and subsystem durability workflows outcomes can be used by other IPE workflows such as vehicle dynamics, brake system engineering, exhaust system engineering, and vehicle NVH and acoustics performance workflows. By collecting all of chassis and suspension strength and durability workflow results, we can perform system abuse analyses during detailed design stage and final validation. So all of the workflows are interconnected with the each design stages very nicely, and also the outcomes of this workflow results can be used by a different workflows we are developing or we already developed. Next slide, please. So the first workflow I want to explain is material calibration. And I will use a little bit of time to explain this, even though the slide itself is very compact, because this is my major. And in this slide, we explained about the eyesight workflow also, but for this presentation, I want to focus on the newly developed material calibration app. We recently developed one app on 3D Experience platform, and we call that as a material calibration. And the newly developed material calibration app on 3D Experience platform provides numerical material model coefficients once user provides material test data and selects the material model. I will call this app as a MCA from now on. And MCA has very convenient tool for collecting and reading material test data, and also has very nice tool to manipulate the test data, such as shifting, filtering, and decimating the raw data. So doing those test data, raw test data manipulation will help the speed up of the calibration procedure. MCA has two modes of material model optimization. One is functional and the other is numeric. In functional mode, MCA implemented closed-loop relation between the test data measure and the stress calculation by the material models, so that the evaluation of response and optimization is very fast. On the other hand, numeric mode uses built-in Abacus backbone to assess the material response, so that the optimization procedure takes longer than the functional mode, but eventually both modes do the same thing. In the current MCA, hyperelastic and the high-perform material models are in functional mode, and elastic plastic, hyperelastic, high-perform PRF, two-layer viscoplasticity, and user materials are in numeric mode. And hyperelastic and high-perform material models are also in numeric mode. First step of material calibration is reading material test data by using MCA's test data reading tool. Then user can select a material model for the calibration. Then the user can optimize the parameters of the material model to get the best fit to the material test data by using built-in optimizer. MCA has 4 different error measures, such as mean squared error, mean absolute error, root mean square error, and coefficient of the determination, which the last one is close to almost the same as the R-square value of the Excel spreadsheet user may very familiar with. And MCA has 7 optimization algorithms currently implemented. Those are Nelda-Mead, Hook-Jeeves, Powell, BFGS, conjugate gradient, particle swarm, and hybrid, which are very popular gradient-based, direct, and exploratory methods. Once the optimization is completed, user can export calibrated material coefficients in the form user can use in Abacus simulations. Next slide, please. The second workflow developed was joint analysis workflow. We used parameterized suspension bushing for this workflow. Inputs to this workflow are initial bushing design, which is parameterized, target stiffness or compliance, and target fatigue life. Through this workflow, user can achieve optimized bushing geometry, which meet the target stiffness and the fatigue life with least material of rubber. First step is creating parameterized bushing geometry by using Abacus CAE, then optimized bushing geometry parameters by using eyesight with multiple objectives such as compliances to major directions of bushing and the least mass of the bushing. Once the eyesight optimization is completed, you can perform Tosca shape optimization to achieve the target fatigue life with least mass with combined usage of Abacus and the FEC rubber. These two separated workflows for joint analysis can be combined into one, or user can perform trade-off analysis to fill the gap of degraded stiffness during the shape optimization for the fatigue life. In any cases, user can obtain optimized geometry of a bushing component for the stiffness and fatigue life by using this workflow, and also those optimized bushing can be used in the follow-on subsystem durability workflow. Next slide, please. Now I want to talk about the component optimization workflow we developed for chassis and suspension in IPE. Here we targeted to optimize the lower control arm, but the same kind of concept can be applied to other suspension components like a knuckle or any other components. From kinematics and compliance analysis by using MBD software such as a SIMPAC, we can get the optimized hard points of suspension system. And we have assigned with the design space for each suspension component. With these information, we can create an initial model as shown in the step 1. And then we perform topology optimization with respect to typical load cases by using Tosca or the Abacus optimization module. We can do the topology optimization, and then on the 3D Experience platform, we have functionality which can reconstruct manufacturable CAD geometry based on this topology optimization geometry. Then we can perform shape optimization to refine geometry of lower control arm for reduced stress concentration on critical region of the component. Through this workflow, user can obtain the optimized shape of suspension component for the typical load cases, starting from the initial design space for the component under fixed hard points of the suspension system. Next slide, please. Then we can perform additional large deformation analysis for the suspension components. In this workflow, we can investigate the large deformation performance of the lower control arm. From the previous workflow, which is a component optimization, we have optimized geometry of the lower control arm with respect to the operational loading conditions. We can perform, additionally, we can perform large deflection analysis on this lower control arm by using so-called RIX method of Abacus to assess the post-buckling behavior of the component. If we want to have increased buckling force and more energy absorption during the abuse load cases, then we can perform the large deformation analysis shown here and tweak the shape so that it improves the buckling force and the energy absorption. We can package this workflow around eyesight again to automatically achieve the optimal design. Next slide, please. by collecting all or some of the previous workflows results, we can construct, for example, half or the quarter suspension model of a vehicle. And in this model, we can now we have optimized the suspension bushing and lower control arm from the previous workflows. We can use Abacus CAE plugin or SIMPAC for this suspension model. Both Abacus CAE plugin and SIMPAC can include the suspension components such as bushing, low control arm, knuckle, tie rods, etc. as deformable bodies. In SIMPAC, we can include those components as flex body by using Abacus substructure generation. Then we can perform quasi-static or even dynamic analysis with many different load cases such as cornering, braking, etc. Here we can also include the tire model. Abacus has interface for popular tire models such as F-Tire, and the SIMPAC has built-in tire model and also interface for third-party tire models. We can perform topology and or shape optimization with load case analysis as shown in step 2. We can also perform fatigue analysis with these analysis results, both Abacus and SIMPAC. Both Abacus and SIMPAC can be combined with FE-Safe nicely to perform the fatigue analysis. Once optimized components are at component level, can be optimized again at subsystem level through this workflow. Next slide, please. And finally, the last workflow developed is a system abuse workflow for the final validation of focused on the chassis and suspension system. We can construct Abacus model for the full vehicle, including FE tires, as shown in step 1, and we can perform transient dynamic analysis with severe load cases such as harsh braking, pothole impact, etc. Then we can investigate the hotspot for the plastic deformation and damage on the material. If the plastic deformation and damage level exceeds the design target, then we can tweak the design variables to meet the target. Again, from the component level, we can optimize the design based on the component level scenarios. And as the subsystem level, we can optimize and detail the design. And then in the final validation stage, we can also optimize again under the system abuse load cases. All of those steps can also be performed by using SIMPAC, but in this slide we just showed the Abacus workflow. That's all I have, and thanks for the attention, and have a great day.
Yep. Thank you very much again. Thanks for joining this eSeminar again. And if you have any questions, feel free to contact us.